Dr. Sander. This is Long Lee, and this is my submission for our individual submission for the final project. So here I'm going to showcase you what the final render for at least my case look like. So here you can see the video. Yep, that's pretty much is the video. So here, let me go over some of the object and texture file if you didn't able to pick them up from there. So some of the 2D asset that we use is the star background, then there is the ship texture, and finally there is also a moon texture, what I didn't apply here because we wanted to have a unique video for each of us. For our 3D access, that will be the first thing will be the ship. So let me go back in the video a bit. You see it kind of here at the bottom because of the way the camera moves. Sometimes you don't really see the ship very well, but if you look at the bottom where my mouse is, you can see the ship right there. So there's a 3D asset. Another 3D asset is the space itself. So right now the camera and the black hole and everything is set inside like a 3D space environment, not 3D space, but like inside like a sphere. So the space, the background is basically mapped into the inside of the sphere, and that's just how we kind of got that effect. And finally, it's also the texture for the moon, which is not on this video. Okay, so let's go over the code that I kind of work on over the project. So I mainly kind of focus on the CUDA code. So here, the first part of the thing, let me go there. This few part, this common now because it's kind of didn't get applied into the final code, but basically it's just a line indicate that if the temperature or basically how close it is to the black hole, it will basically output a certain color. The closer it is to the black hole, the brighter or the hotter it gets. So that's why this is kind of like a pseudo code where temperature from 6,000 to 10,000, the bright orange over there. Yeah, this is basically just pseudo code, so I want to skip over that. And let's go over the first bit of true code. This will be basically the intersect display. This part right here, that just declare a device function for CUDA execution that return a boolean indicating whether the intersection occur. It would then compute a dot product. It calculate a dot product of this normal and the ray direction. This value determine if the ray is parallel to the plane. It will then check the oh wait, yeah, that top right here. Return for here. This part will basically, if the absolute value of the denom is very small or below the threshold, the ray is nearly parallel to the display, so there will be no meaningful intersection exists, and the function return false. It would then compute a formula that just calculate where along the t parameter along the array the intersection with the plane will occur. And then if the intersection basically is behind array, or if t is negative, the intersection point lies behind the array origin, so it is not visible or relevant. Henceforth, it will return false. Else, it will store the computed t in the output parameter, compute the actual hit point on the plane as the origin plus the array direction scaled by t, and store it. So yeah, that will return 2. Moving on to the intersect triangle, this part. This is just basically a CUDA device function that returns whether an intersection occurs. The float h1, h2, that just calculate the 2 edge vector of the triangle by subtracting vertex precision. The float 3h right here, that will compute the cross product between the ray direction and h2. This just help for later calculation to determine, yeah, just stuff like that. And the float A right here, that's just a dot product between H1 and H products produce the determinant the magnitude of a determinant if the ray is nearly parallel to a triangle plane. And then basically if A is near 0, the triangle is edge on to the ray and no intersection is possible. This will basically inversion, float F is basically an inversion is used to quickly compute the pericentric coordinate. It will this factor is just used to determine how far along and within the triangle the intersection might be. The float U, this part will compute U and then check if it's lie within the valid range. If not, the intersection point lies outside the triangle. And then for float 3, this is just another helper vector calculated to aid in determining the second pericentric coordinate. It will basically calculate V and check that it is non-negative and that the sum U plus V does not exceed 1. If the check fails, the hit point is outside the triangle. This right here, just compute T, which tell how far along the ray the intersection occur. If T is greater than a small epsilon, the function store the result and return true, or else it just return false. Moving on to the intersect accretion disk. Similarly before, this is just a CUDA device function that return a boolean indicating whether the ray intersected disk. Now this center and this normal, this is assumed to be center at the origin and lie flat at the x and z plane. The float t right here, and if this core intersect this plane to see if the ray even meet the infinite plane of the disk. If not, the function return false, meaning no intersection at the disk. Moving on, let's go to this part right here. Yeah, this will compute the distance from the disk center to the hit point. It will then check that the hit point lie between the inner and outer radius of the disk. If not, the ray misses and just miss. It will then, I think these two will calculate, normalized radius will tell how far along the inner to the outer edge the hit point is. And inverse radius right there just is the inverse, meaning is the highest 1 at the inner edge and the decrease outward. It will then calculate the temperature at the hit point. Let's go to emission right here. This emission is measured brightness at its highest in the inner edge, decreasing outward following a squared law. The float angle and float pattern. The angle of the hit point in the disk using, I think, a tangent 2f is calculated, and a sine function modulate by the angle, and distance create a periodic variation. This pattern basically value slightly modulate the emission, and emissivity, I think, by like 20%, and adding to basically like a visual texture of the disk. It will basically then save the intersection distance t and return true to indicate a successful intersection with increasing disk. And then finally, not very finally, the trace race. I'm just gonna skip over this first part because similar to before, that's just the CUDA stuff that I require. Yeah, moving next. Wait, where is? Let's move down a bit. Yeah, in X and Y. Let's start here. So this part just determines the pixel location X and Y from the block and thread indices. It will check that the pixel lies within the bound of the rendered image. If not, the thread does not exist or the thread exists. These two chunks right here just basically unpack the camera setting. It will retrieve the camera position and orientation vector, forward, right, upward, whatever, and also the FOV value to just for later use because we basically that's how we're gonna compute using the camera. And then the accretion disk parameter is similarly to the camera parameter. This just define the inner and outer radius of the accretion disk as multiple of the event horizon radius. And dictateness is defined by the vertical extent of the disk, although this isn't used further in the, yeah. And then this will be final color. Yeah, similarly, this just compute the ray direction, and that if the fell into black hole is false, it's just red, basically just a brightness. Let's see. Free flow aspect. But yeah, that's pretty much all the code that I kind of did. Thank you very much.